In the last lecture, I defined the rotational inertia, as referred to as the moment of inertia, which is a quantity that describes an object's resistance to angular acceleration. Hopefully we're getting the idea here that I'm transitioning from a bunch of quantities that I'm very familiar with in their translational context, and I'm finding their rotational analogs. For example, position, velocity, and acceleration are replaced by angular position, angular velocity, and angular acceleration. Well, there was a little demonstration, it was quite fun, where I had two rods that had the same mass and therefore the same resistance to translational acceleration. But when you hold them in your hands and you turn them, you find that one is more difficult to turn than the other. That is, their resistance to rotational motion is quite different than their resistance to translational motion. So I need a quantity that describes that, and that quantity is the moment of inertia, which we give the symbol I, and in its integral form, which I guess you could make an argument is the most general form, is r squared dm. It's the quantity that I have to compute. There's no, in the case of the inertia, you might call it translational inertia, but mass. I can simply take an object and put it on a pan balance and it tells me what the inertia is by comparing the inertia of the object to the force of gravity. But in the case of moments of inertia, I actually have to compute them for various objects. And search through your textbook. I used to remember what page in the particular textbook you use, but in every physics textbook on this level, there's a page that lists the moment of inertias of common regular objects. Things that I would find in problems. You would not be surprised. Things that rotate, rods, spheres, rectangles, triangles, all sorts of regular geometric shapes that might be in a situation where they have an angular displacement in space. So knowing their moment of inertia is worthwhile. So what I'm going to dedicate myself to this morning is simply computing the moments of inertia for a couple of particular cases. I will not go through and compute the moment of inertia of every object that you'll ever encounter. The reason is this definition of moment of inertia is cast as a calculus relationship here, and finding the moments of inertia of regular objects is really just a calculus exercise. It's not really an exercise of physics, a mathematical exercise. So I'll do a few to familiarize you with the technique, but as you go forward, even imagine yourself someday forward in your career needing a moment of inertia, what you would do is you would look up that moment of inertia in a textbook. You wouldn't go through the calculus machinations to discover it. That problem is solved one time and then it's done forever. In fact, on our exams, in our physics, it's extraordinarily rare that you would be expected to compute a moment of inertia from scratch. Typically, on our exams, they're given to you outright. And you're very rarely even expected to memorize them, although there are a few moments of inertia that I carry around in my head because I find it convenient for my problem solving just to be aware of what they are. And four of those moments of inertia, you'll see in today's description. So what I'm going to do is apply this integral law to two cases right off the bat that are spectacularly simple. And give us immediate results that we're going to want to internalize and keep on hand. Let me first consider the moment of inertia of a point particle going around in circular motion. I don't care if it's uniform circular motion or non-uniform circular motion. That doesn't matter. What I'm interested in is its resistance to angular acceleration. And so, well, certainly that angular acceleration would imply some tangential acceleration, which means it's not uniform circular motion. But I'll draw a familiar diagram here, which is a circle, and that's a pretty nice circle. Thank you. And here's, well, I work out, so here's the mass here, and it's going around in circular motion, so it has some velocity I don't care about, but I'll draw the velocity anyway to imply that there's motion involved, so it's sort of a dynamic thing. And the circle has a radius r. What shall I call it? I'm going to call it lowercase r. I'm going to try to play along today and use lowercase r's all the time. I sort of switch back and forth between lowercase and uppercase r's. My general rule for that is that I'll typically use a capitalized quantity for a quantity that doesn't change. And certainly in circular motion, the radius of the circular motion doesn't change. But you'll see these things go back and forth in textbooks and lectures and things that you see. I'm just going to call it r right now. And then I want to apply this integral law to this situation and ask the question, what is the moment of inertia of a point particle? You might be curious at this point, and if you're thinking this is completely appropriate, why do I want to know the rotational inertia of a point particle? A point particle has inertia. It has a mass. Well, a little bit later on, once we've fleshed out some of our rotational dynamics, I'll be able to show quite clearly how these two ideas are ultimately equivalent to each other in the case of a point particle. But for the moment, let me just humor my definition of moment of inertia. How shall I now apply this? Well, let me go. Equal. Because I have a point particle traveling around in circular motion, this radius is a constant of the motion. As time goes on, the radius remains the same. But that's not the point that I'm interested in. What I'm interested in is that every little bit of the mass of the point particle, that is, if I were to break the point particle up into differentials of mass, which is a curious thing because my point particle technically has no physical extent. It is itself an infinitesimally small mass. But if I was to divide it up into differential masses, every single differential mass is the same distance from the axis of rotation. Putting that in a more casual way, all of the mass is the same distance from the axis of rotation, and therefore r squared comes out of the integral. And so I simply end up with the integral of dm, which we know is quite trivial. The integral of dm naturally is the mass. And so I find that the moment of inertia of a point particle, so I guess I start giving these things names, and I call it I don't know what to call it, I sub p, I don't know, for I of a point particle. I'm going to call it I point. I'm not wild about that, but the moment of inertia for a point particle is just mr squared. And I notice that it has the units that I expect of a moment of inertia, kilogram meters squared. All of the moment of inertias that I derive, all of them, should have the same units. That's kind of useful to you to know in case you're asked to derive a moment of inertia. You get to the end and you wonder, is this the correct answer? Well, check the units. They should, at a minimum, the units should be correct and be kilogram meters squared. So that's the moment of inertia of a point particle. It's absolutely trivial. It was an easy get for me. The next moment of inertia that I'd like to calculate is the moment of inertia of a hoop. Like, for example, my bicycle wheel that I had out here and I was spinning in the last lecture. Most of the mass of that bicycle wheel is at a constant radius around in a circular hoop type shape. Now, it has spokes and whatnot, and I have to consider that if I really wanted to know the moment of inertia of it. I would have to consider all the spokes and things like that. But let me consider now a mass in the shape of a hoop. So I'm just going to, it's difficult here. I'm drawing a circle, but this circle is now a massive circle. It's a circle of mass m. Am I going to make it extra thick? What's going to be a problem? We're all sitting here watching me make the circle extra thick and not doing a very good job of it, actually. Do you like it? Okay, circle's extra thick now. But it has a total mass m. In a sense, it's this point particle here, right? Smeared around the whole thing. Smeared around the whole thing. And it's done in such a way that it has a radius r. And now I'm going to apply my integral law again. I'm trying to do everything on one board this morning, and I'm doing myself a disservice in this regard. So I'm going to calculate the moment of inertia. I'll do it down here. The moment of inertia of this hoop, so I'm always going to refer to it as a hoop. So moment of inertia of the hoop, I hoop, is the integral of r squared dm. Well, here, in this case, I actually have need to divide the hoop up into differentials of mass. I have to define what is dm, and that's easy to do. All I have to do is make a little slice out of this, boom, boom, like that, and say there's a little differential of arc here, length here, maybe it's ds, the differential of arc length, that contains a differential of mass dm. And then a thing becomes immediately apparent. Immediately apparent. Every single dm is at the same distance from the axis of rotation. Every single dm is the same distance from the axis of rotation. And so once again, the r squared is a constant and comes out of the integration, so it's r squared, the integral of dm, which once again gives me the same result. That's right. The moment of inertia of a hoop and the moment of inertia of a point particle are the same. It's got the same moment of inertia. And that's not surprising, because the key feature of the moment of inertia, it depends not only on the mass, but on how the mass is distributed in space, according to the axis of rotation. Well, in the first case, the point particle, the mass is all the same distance from the axis of rotation. In the second case, the hoop, in a way that matters, all of the mass is the same distance from the axis of rotation. So it doesn't surprise me at all that it has the same moment of inertia. So there are two examples of finding moment of inertia, and I get two trivial results. Those trivial results will come up in problem solving all the time. It's worth your while just to appreciate the fact that the moment of inertia of a point particle is mr squared, and the moment of inertia of a hoop is mr squared. You should just have those automatically right off the top of your head, because it will come. Your problem solving will be replete with those moments of inertia, because there are common examples that contain them. If the radius is large compared to the size of the car, then yes, I can treat it as. But the point particle that I'm imagining is one single point in space. So it's an approximation always. If the radius were small compared to the geometry of the particle that's going around, whatever it is, an automobile or whatever you choose, then I would have to perform a more sophisticated integration, because the near part would be much closer to the axis of rotation than the far part, and it matters. And so I would have to perform an integration in order to figure that out. Yeah?
The hoop, if you were to make that three-dimensional, would it be the same idea, like if you had like a empty, like...
That is, if it were, you worry about extruding it out into this. Oh, a hollow sphere I'd have to calculate differently. Yes, that hollow sphere has a different moment of inertia.
Okay.
But a tire, so can we call it the thickness? If I extrude that hoop out of the board, that thickness does not matter to the calculation, because the radius is from the axis of rotation. And if I extend the axis of rotation out of the board, then that radius vector always points from the axis. It's all pieces of mass are the same perpendicular distance from the axis of rotation. And so your question has forced me to say something that I'm going to say later on, but probably should have said earlier on, is that it's the perpendicular radius from the axis of rotation that matters. And so it doesn't matter how thick this hoop gets, its moment of inertia will still be mr squared.
So if you have a hoop that's, I don't know, as long as it's kind of uniform, right?
Mm-hmm.
You can make it so the middle, the radius is just tiny, 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 and its moment of inertia will still be mr squared. It won't be treated as like
it's the same as the point that I made with Blake's. If the radius becomes small compared to the thickness of the hoop, now I have to perform a different integration. That is, this moment of inertia assumes that all of the mass is at the same radius. And if the radius is large, then differences in the radius are irrelevant. But if the radius is small, then differences in the radius become significant. And if you turn to that page in a textbook that has a table of moments of inertia, you will find that there's a difference between the moment of inertia of a hoop and the moment of inertia of an annulus that has an interior and exterior radius. That has a different moment of inertia, because the thickness of the annulus is significant compared to the radius overall. And so that has a different moment of inertia than the hoop does, right? The hoop and the point particle are simply the most common approximations that we use in problem solving, right? Most common approximations that we use. We can get into, but not to worry, if I run into something that's more significant, that is not one of those common approximations, I can compute what the moment of inertia is of anything by performing the integral, which I may not want to do. These two integrals were extraordinarily easy to compute. Now let me do two examples that are still quite simple, but not trivial, not absolutely trivial. Requires some discussion. Yesterday I distributed around the room a pair of rods with mass distributed along a length. What I'd like to do is compute the moment of inertia of a uniform rod. Now, one of those rods that I handed around had the mass distributed uniformly along its length. The other one did not. I wonder, we didn't actually talk about it. Does anybody realize now, after thinking about it, what the trick is? Like why they had such different moments of inertia, those two rods that outwardly are identical? Yeah. The one rod has the mass distributed uniformly along the length, and the other rod has the mass all the way at the ends, far away from the axis of rotation. And when you move the mass away from the axis of rotation, the rotational inertia, the resistance to acceleration, increases. But let me consider now a uniform rod and try to compute what the moment of inertia is for a uniform rod. So here we go. And the next two examples that I'm going to do are essentials. The next two examples that I'm going to do are essentials. Here I go, finding the moment of inertia of a uniform rod about its center of mass. That's a long title.
Is that the name of it?
Yeah. The moment of inertia of a uniform rod about its center of mass. So what I need is a uniform rod, so I'll draw here a rod. Looks very identical to when I was doing center of mass calculation. It's just a rod, and the mass is distributed uniformly along its length. The difference between doing this sort of calculation, well, many differences, but the most important difference, I think, of doing this calculation as opposed to a calculation of locating the center of mass position is that in this calculation, I need to define the axis of rotation. I need to state clearly About what axis am I talking? Because an object will have a different moment of inertia depending on the axis of rotation. You're about to see that very explicitly as I go through these calculations. But for the moment, let me say that what I would like to do is find the moment of inertia of this rod through its center of mass. I'm going to find the moment of inertia of the rod through its center of mass. And since the mass is distributed uniformly along the rod, I've already discovered that its center of mass location is the center of the rod. But my requirement for performing the integral is that I choose the axis of rotation to be the origin of my coordinate system. It's a requirement. I must do that. The axis of rotation chosen as the origin of my coordinate system as I perform this calculation. So now I'll figure out what is the moment of inertia of a rod about its center of mass. And so I compute the integral, r squared dm. Well, I have to define the differential of mass. And so I'll divide the rod up, and this should be very familiar to you because it's very much like the center of mass calculation. I'll divide the rod up into lengths dx, each of which contains a mass dm, and is at a position x in my coordinate system. Because in order to perform this integral, and by the way, my definition of the moment of inertia, of course, is three-dimensional. R can be a three-dimensional vector. Let me break it down into one dimension. It's perfectly legitimate. We've done many times. Is the integral of x squared dm. So I make it a one-dimensional integral. But now what do I do? Because I need to perform the integral of x with respect to, well, x squared, with respect to dm, I need the relationship between the two. Hopefully you'll be comfortable with me immediately asserting that this rod has a certain mass per unit length, lambda, linear mass density, which is the mass of the rod divided by the overall length of the rod. Let me call that L. The overall length of the rod. I'll call that capital L, which of course is the same as the differential of mass divided by dx, is an argument that we made previously. The differential of mass divided by dx from a previous argument. So I can make a substitution in my integral that the differential of mass is equal to lambda dx, familiar substitution. So here in my integral where I have dm, I'll replace it with lambda dx, but of course lambda is a constant with respect to position, which it need not be. It is in this example because I don't want to be distracted by non-uniformly distributed mass. But maybe the mass of this thing is not uniform. Maybe the mass is not uniform, but in this case I'm assuming that it is, so that lambda is a constant. So my integral for the moment of inertia, I, becomes lambda times the integral of x squared dx. I want to take a moment now to consider what are the limits on my integration. Because of the way that I had to choose my coordinate system, with the origin of the coordinate system located at the center of mass position, which is the axis that I choose, the limits on the integration have to be from negative L over 2 through 0 to L over 2. Negative L over 2 being here on the left-hand side of the rod, L over 2 on the other side of the rod, integrating from negative L over 2 to L over 2. Did I say something wrong? Okay. Integrating from one end of the rod to the other. Well, the integral of x squared is quite simple. It's x cubed on 3, isn't it? So I have lambda out in front here. X cubed, that's a 3. I'm just a millisecond ahead of myself. X cubed over 3, evaluated from negative L over 2 to L over 2. Well, let's work this out. When I evaluated L over 2, I'm going to cube that. And so I have 2 times 2 is 4 times 4 is 8. I'm having one of those moments right now where I feel as though I've made a mistake, but I couldn't possibly. It's completely straightforward. Why is this bothering me? It shouldn't bother me. Well, I'm just going to play along. I'm not getting the result that I expect. Oh, wait, yes, I am. See, every once in a while I suffer from the same problem that students often do, is that my anticipation of the result is causing me to question what I'm doing in the moment. And that can happen to us at all levels, like it happens to the best of us, or so I'm told, and it happens to students all the time. So I just have to go along with it. So I have lambda. Well, this is going to be evaluated at L cubed on 24. And that's really what bothered me. Because 2 cubed is 8. 3 times 8 is 24. Minus the same thing evaluated here at negative. But it's cubed. So the negative sign doesn't become a positive sign. It stays negative. So it's minus. No, that's not true. So it's positive. Right. That's what I meant. I just said out loud and then questioned the same thing that I just said. I wrote squared. You see what's happening to me, Jules? Thank you. I'm all up inside my head here. It's bizarre because I'm getting exactly the result that I wanted, but I'm fighting it. 1/24 plus 1/24 is 1/12, which I know is exactly the answer that I want. So I have lambda L cubed on 12. Well, I'm not going to leave the lambda in there. Remember that because the mass is uniformly distributed, lambda is equal to m over L. So making that replacement, I get the very well known to me and every other physicist on the planet result that the moment of inertia of a uniform rod about its center of mass is 1/12 ml squared. Notice it has the units that I expect from moments of inertia. Kilogram meters squared, kilogram meters squared, kilogram meters squared. But it has some fractional nonsense out in front, and that's the typical look of a moment of inertia when I calculate. 1/12 ml squared is the moment of inertia of a rod about its center of mass. Really critically important, that last bit of the statement. It's the moment of inertia of a rod about its center of mass. What would happen if I did the same calculation again, but chose a different axis of rotation? Well, that's the very next thing that I'm going to do. This calculation, absolutely essential that I be able to do that, finding the center of mass of a rod of uniform mass distribution. Finding the center of mass, finding the moment of inertia about the center of mass of that rod. Now I'm going to do the calculation again, but this time I'm going to find the moment of inertia of this rod, same length, same uniform mass distribution, but I'm going to find the moment of inertia of the rod about one end of the rod. Because I can certainly take a rod and rotate it about its center, but I can also take a rod and rotate it about its end. Yes. Yes. The moment of inertia of a uniform rod about its end. Perhaps we'd rather call it Susan.
You just said like top heavy rod.
But it's not, because the mass is uniformly distributed. You're just holding it at the end. So like a baseball bat, kind of. But a baseball bat's not actually swung around its end. Close. But I'll have to help you out with that problem there, Blake, where it's not quite what I want it to be. So I'm going to solve that problem for you in just a minute. So stay tuned. So now I'm choosing my axis of rotation to be the end. That'll be the origin of the coordinate system. So what difference could this possibly make? Well, it makes a physical difference, and it makes a calculus difference. Let me proceed quickly because I know how this goes. The moment of inertia, I, is equal to the integral of r squared dm. But of course, I'm doing a one-dimensional integral, so let me make it x squared dm. But I need a relationship between dm and x. Well, the mass lambda is uniformly distributed. That is, it's m divided by L is equal to dm divided by dx. Shall slow down? Why should I? I'm doing exactly what I did here. There is no difference between these two. Not yet. And that gives me a relationship between dm and dx, which is the differential of mass is equal to lambda dx. And so I make that replacement in my integral, so the moment of inertia becomes lambda, which is still a constant of the thing, the integral of x squared dx. And now I come once again to this moment where I consider the limits of integration. And it's the limits of integration where I get my different result. Because now, since I've chosen I should mark this up as well here with a little, I'm just making some additions here. There's a little dx that contains a dm, and it's a distance x from the thing, just to make the diagram complete. So my limits of integration, I'm going from 0 all the way to the end of the rod. So the limit of integration is now 0 to L. When I perform the integration, I get the same result. I'm going to get lambda times x cubed over 3, the quite simple result of that integration, but evaluated from 0 to L. And so what I get for my moment of inertia is lambda times the quantity L cubed over 3 minus 0. minus 0. Which gives me lambda L cubed on 3, and making the replacement that lambda is m over L, this becomes 1/3 m L squared, because the L in the thing cancels. 1/3 m L squared. So you see what's happened. When I compute the moment of inertia of the uniform rod about one end, I get a different fraction out front. I still have my ml squared, but I get a different fraction out front. Notice that the moment of inertia about the center of mass position is smaller than the moment of inertia about one end. And so the moment of inertia about the center of mass is the lowest moment of inertia that any regular object can have. It's the smallest moment of inertia that it has. And the moment of inertia about any other axis is in fact larger. And so whenever I consider a regular object, and if I go back to that table of moments of inertia, whenever I consider a regular object, I have to also ask what axis of rotation. And so when I go to that table, I'll see, yes, there'll be a sphere, but there'll also be a sphere about its edge, about its center, about other locations. But it turns out that there's a generalizing principle that will allow me to derive some moments of inertia if I already know the center of mass moment of inertia. It's a theorem that's known as the parallel axis theorem. And all it requires is that I know the moment of inertia about the center of mass, which, for example, for this rod, I know. The moment of inertia of a rod about its center of mass is 1/12 mr squared. And so I'm going to take advantage of that to find the moment of inertia about any other axis, like, for example, one end. And the way that I'm going to do that is do a little bit of fundamental derivation. This is not essential that you know this. It's just one of these things where the parallel axis theorem, if you want to give this a label in your notes, the parallel axis theorem seems a little bit magical, and I don't want you using any bit of physics without explaining to you why it should be so. So consider the moment of inertia here, I, is equal to the integral of r squared dm. And I'm going to do a little bit of derivation with it. But I'll also need a diagram. Should I use the rod as the diagram? Should I use the rod as... No, space peanut. Space peanut. So here is my coordinate system. I'm going to regret this diagram, I think. Here's the x-axis, here's the y-axis, and here is the space peanut. Oh, geez. Arbitrarily shaped space peanut, and notice I did not put the center of mass position at the origin of my coordinate system. I don't have to do that. But there it is. Let's imagine that that's the center of mass position. Somehow I've magically found it. Let's imagine let's imagine that it's at the end of where I intended to draw my arrow. That's the center of mass position, and that's the radius r. The point is this: the location of any point of mass on the object in space is defined by the position vector r. Here I'm doing it in 2 dimensions. I could do it in 3. It would just complicate my algebra. The point is this: that I can write my moment of inertia integration as the integral of x squared plus y squared dm. Because, of course, r squared is equal to x squared plus y squared in this coordinate system. It's perfectly legitimate. But now what I'd like to do is, instead of using this coordinate system, which is the center of mass position here, instead of using that axis of rotation, I would like to use an axis that is parallel to it. That is, I want to know, perhaps I'm interested in this edge over here, and I want to know what is the moment of inertia about this edge. That is a distance d from the center of mass axis. Do you see? So I want to know what is it about that axis. Well, break out the integral and reintegrate the thing. It turns out I don't need to, because here's what happens. This is the moment of inertia about the center of mass. The moment of inertia, now that I've displaced the axis of rotation, is going to be the integral of, and watch what happens. In order to displace that axis over, I have to take the x value of every single point and move it over a distance d. I have to take the x value of every single point and move it over a distance d. So what I have is x plus d squared plus y squared dm. See, all I've done to calculate the new one is I have to move every x point over a distance d. It's translation. It's translation. Well, do a little bit of algebra to this. Start to flesh it out. This is the integral of, I'm going to FOIL this thing out and see what I get. Well, naturally what I get is x squared plus 2xd plus d squared, and then I have the plus y squared left over, dm. It's the sum of 4 integrals. Well, it's the integral of a sum of 4 terms, and so I can write it as 4 integrals. But I'm actually going to write it as 3, because I'm going to write the integral of x squared plus y squared dm. See, because I take my x squared and my y squared, there they are right there, I'm going to bring them back together again. X squared plus y squared dm. That's one integral. Plus d squared times the integral of dm. That's one integral, because there's d. And the last integral is 2d integral of x dm.
Are they all having that center of mass little thing that that second line had?
No, because you're not trying to find it for the center of mass.
Right, but excellent observation, because this right here is the center of mass moment of inertia. So I'm going to identify what these terms are. This term here is the center of mass moment of inertia. X squared plus y squared dm, that's the center of mass moment of inertia. Plus, this term, d squared, the integral of dm, that's obvious. If I integrate dm, I get m. That term is m d squared. And that last term, troubling, is the integral of x dm. Wait a second, I know what that is. Isn't that the center of mass position? Which can arbitrarily be chosen as 0.
That's the integral of SDM.
Okay, yes. So it's not the center of mass position. It's actually what's called, this integral is technically what's called the moment. Not the moment of inertia. It's technically called the moment. But point is, the integral of x dm works out to 0 because it's proportional to the center of mass position, which is in fact at 0 in this coordinate system. So that's 0. And so I have the parallel axis theorem now derived for you. That the moment of inertia of a regular object about an axis that is parallel to its center of mass axis is equal to the center of mass moment of inertia, ICM, plus the mass times the distance between the axes squared. The distance between the axes squared. That's a very, very useful theorem, the parallel axis theorem. Let me show you really quick an example that will clarify that this is true. What if I wanted to know the moment of inertia of a rod about one end? Shall I already know what it is? It's 1/3. Well, let's say I didn't know. The moment of inertia of a rod about one end would be the moment of inertia of the rod about its center of mass, which in principle I do know, 1/12 ml squared, plus the mass of the rod times the distance between the center of mass axis and the new axis, which is the end of the rod, squared. That distance is L over 2, isn't it? Because I've got to go from the center of the rod to an end. That's L over 2. So that is L over 2 squared. Well, that's a 12th plus a 4th is 1/3 ml squared. So I went through the trouble of integrating to find the moment of inertia of a rod about one end, but I could have found it using the parallel axis theorem because once I know the center of mass moment of inertia, I can find any other moment of inertia about an axis parallel to the center of mass axis simply by applying the parallel axis theorem, which means if you asked me off the top of my head if I know this moment of inertia or that one, if I have them memorized for my convenience, you'll find that I have memorized the center of mass moment of inertias of many regular objects. I need not memorize the moment of inertia about some other axis because I can always parallel axis theorem and shift that moment of inertia this way or that in order to get a moment of inertia that I'm interested in knowing.